Good evening and welcome back to Thought Leaders, the lecture series hosted by Space Center Houston and sponsored by UTMB Health. I'm Tarek Thomas, Associate Vice President for Facilities Design and Construction at UTMB Health. Tonight, we're talking about space architecture. Architectural ingenuity will be key to the success of America's return to the moon and future travel to Mars. NASA scientists are already hard at work to design human-centered habitats that can support deep space travel and interplanetary living. Human-centered architecture is a concept familiar to us in healthcare. There's a field known as architectural medicine that works to create more home-like medical facilities that promote relaxation and recovery. But our job's a lot easier. We have a gravity and atmosphere on our Earth-based projects. Space architects likely share some of the same goals, designing safe and comfortable, efficient, and restful places for our future space travelers. We'll hear more about some of the unique challenges and innovative solutions from today's talented panelist. I'm glad you have tuned in. Join me in pulling up a comfy chair as we learn more about designing for humans in space.
Thank you for joining Space Center Houston's Thought Leaders Series discussion, Space Architecture, presented by the University of Texas Medical Branch. I'm William T. Harris, President and CEO of Space Center Houston. We're a nonprofit and immersive space exploration learning destination with a purpose of bringing people and space closer together. We're also the official visitor center of NASA Johnson Space Center and help share the story of human spaceflight with more than 1.3 million visitors annually from around the world. Our Thought Leader series brings you space and science experts from around the world to provide insights and perspectives on space exploration. Space architecture refers to the specialized field of designing and planning structures, habitats, and environments for human activities in outer space. This field is increasingly relevant as humanity aims to establish a more permanent presence beyond Earth, including on the Moon and Mars. As we advance the Artemis missions, NASA's space architects are working diligently to create innovative solutions that optimize safety, efficiency, and comfort for space travelers. At Space Center Houston, we believe science learning and space exploration are for everyone. We're proud to celebrate 30 years as a hub of understanding space exploration for the Houston region and beyond. We want to inspire you through our immersive and authentic science learning exhibits and spacious outdoor experiences. To get the most from your experience at Space Center Houston, please purchase your time tickets online ahead of your visit to save on general admission. To plan your journey with us, go to spacecenter.org for additional tips on planning your visit and maximizing the fun. And now on with our panel, Space Architecture, presented by UTMB. Today we're joined by Larry Toups, an adjunct associate professor at the University of Houston College of Engineering at the Sasakawa International Center for Space Architecture. Larry Toups attained his bachelor's in architecture from the University of Houston and master's in space architecture from the University of Houston Sasakawa International Center for Space Architecture. From 1988 to 1994, Larry served as a senior engineer with Lockheed Engineering and Sciences Company at NASA Johnson Space Center, where he provided technical support for JSC's new initiatives office and systems engineering of habitats and planetary systems. After joining NASA in 1994, he worked in the International Space Station Program Office and assumed the role of Habitability Systems Lead in the ISS Vehicle Office and was responsible for human factors requirements. Our next speaker is Chris Kennedy. Chris has been a licensed architect in Texas since 1995 and earned a bachelor's degree in architecture from University of Buffalo and a Master of Architecture Design from University of Houston. Chris worked as a space architect for 30 years at NASA Johnson Space Center, retiring at the end of December 2017. He's a recognized space architect and exploration habitat expert among international partners in the aerospace industry. Prior to designing space systems at NASA, Chris worked at numerous architectural firms in New York and Texas. He is the founder and president of TechNet Architects, LLC, and an adjunct assistant professor of space architecture at the University of Houston at the Sasakawa International Center for Space Architecture. Chris also worked in the JSC Engineering Directorate for 25 years, and then the Human Health and Performance Directorate for his last 5 years. Chris has held key leadership and management positions at NASA, such as project manager of the Deep Space Gateway Habitat Internal Architecture Project, key strategy roles in the Human Health and Performance Directorate, deputy project manager of the Deep Space Habitat Project, manager of the Habitat Demonstration Unit Project, supported the Constellation Lunar Surface Systems Habitation Team, Lunar Mars Architecture Team, ISS Hardware, and led technology strategic roadmaps development, among many other leadership positions in numerous space design projects. Chris has worked on over 45 NASA design projects and published over 60 papers in the field of aerospace human spacecraft design. Chris has numerous technology briefs and 2 NASA patents, one of which is the TransHab. It's an inflatable spacecraft that won the 2017 Government Invention of the Year. Our next panelist is Brett Montoya, who is a lead space architect in the Center for Design and Space Architecture at NASA Johnson Space Center. Brett provides architecture and design services such as concept development, spacecraft layout design, mock-up design and fabrication, and human-in-the-loop, or HITL, testing for NASA's human spaceflight programs. Brett obtained his master's degree from Sasakawa International Center for Space Architecture in 2017 and currently works in the NASA Human Health and Performance Directorate. Our final panelist is Paolo Mangili, a space architecture graduate student and research assistant at the Sasakawa International Center for Space Architecture at the University of Houston. Paolo holds a Bachelor of Science in Product Design from the Polytechnic University of Milan and describes himself as a lifelong space enthusiast. His projects combine disruptive design and a multidisciplinary approach with the idea that any proposal leads to positive differences in the universe. Originally from Italy, Paolo decided to study space architecture in the United States due to his belief in the peaceful utilization of outer space for the benefit of humanity. We have an amazing panel of specialists today. Thank you all so much for joining us. We'll now hear from our first speaker, Larry Toups.
Thank you, William. Let me start by thanking Space Center Houston for inviting me to participate in such an exciting and relevant discussion today. I wanted to use the next few minutes to give you a glimpse at my background, but also how that shaped my definitions, basically, of space architecture. In my case, the definition of space architecture revealed itself to me while working in the different project areas of my career. My journey started in 1975 when I graduated from the University of Houston with a 5-year professional undergraduate degree in architecture. Yes, that infamous year that brought us the #1 hit by the Bee Gees, Jive Talkin'. I practiced architecture for the latter part of the 70s and through the 1980s. That magical time that brought us boom boxes, Rubik cubes, and DeLoreans. Seeking new challenges in the late 80s, I enrolled in a relatively new program at the University of Houston that looked at the relationship of architecture in extreme environments, mainly space. This was SIXA. So in that year, 1988, Skywalker was born. Over the course of 30 years, I first worked at Lockheed looking at what was required for a more permanent human return to the moon and Mars. That part was part of a presidential mandated study known as the Space Exploration Initiative. After accepting an invitation to join NASA in 1994, I became part of the incredible joint NASA-Boeing team that produced the International Space Station. And for the last 14 years of my career, I returned to looking at a return to the surface of the moon and Mars. That overall experience timeline started with a focus on the lunar Mars surface, then to low Earth orbit, and back to a focus on planetary surfaces. Currently, I now help mentor young students at SIXA sharing those experiences. Let's start looking at the basic challenge of space architecture. I'd narrow it down to the constraints imposed by the transportation system to get there. particularly in designing and constructing a place for astronauts to live on a planetary surface, their house. Compared to building a house on Earth, consider that all the building materials, the construction equipment, the power and life support equipment, as well as the workforce to build it, must fit on one truck. I've selected 3 themes that are defining aspects of space architecture based on my real-world experience while working with NASA. The first is the importance of the integration of multiple systems. Simply put, planning the delivery and connection of diverse pieces of hardware to create a space vehicle or even a lunar base. During the Space Exploration Initiative, I developed a planning document that looked at delivering multiple pieces of hardware, such as rovers, habitats, and solar power arrays, to the moon's surface, to the same location. This would be done over the course of multiple flights over time. Consider a phased approach, similar to how an urban planner strategically plans a new subdivision, a new neighborhood, or even an entire city. You can see from the renderings on these slides that laying out a base on the moon can take many different forms. Incorporating the use of inflatables or hard-shell space station-derived modules, to habitats that land and stay on the lander, or perhaps even move from place to place rather than staying in one location. I had the fortune to be the NASA lead on a joint project with the National Science Foundation and ILC Dover, the maker of the spacesuits that NASA has used over the years. This was another example of integrating multiple systems, plus this time introducing autonomy of those systems as well as the use of inflatable technology. The structure arrived at McMurdo Station in Antarctica in 2 pieces after shipment by container ship from Port Hueneme in California, followed by a plane ride to the ice runway at McMurdo. The 2 pieces were joined and inflated in less than 1 hour by 4 people. The interior and exterior was then outfitted with lights and flooring and over 200 sensors to monitor the behavior of the structure remotely from right here at Johnson Space Center. The second theme important to space architecture, in my opinion, is human-centered design. Here you see how astronauts slept on the space shuttle, basically accommodating people within a machine. From the lessons learned from Space Shuttle, as well as Apollo, we came to realize that the human is the central as well as the primary system in the design process for habitats such as the International Space Station. When I was the Flight Crew Systems Subsystem Manager for the ISS, my team was responsible for providing dedicated crew quarters. In the early part of the assembly sequence, we had 3 crew aboard, but only 2 dedicated quarters. So we worked with our Russian counterparts to design a temporary 3rd quarter. The process involved directly working with the future increment crews to determine the design. They were center to the approach. This led to a human-centered design of the eventual quarters that the crew felt ownership with and met their needs of privacy. Fast forward to 2019 and the evaluation of possible habitats for Gateway, crew evaluations were essential to that process. We had the crew simulate the use of the habitat on a daily basis. Again, a very human-centered approach to the evaluation and the eventual design of those habitat concepts. The third and last theme of space architecture, in my opinion, is the importance of living off the land. Prudent use of resources available of where you are going, whether it be the moon or Mars. One example is the use of the lunar regolith. Tests have investigated additive construction with centered regolith to create useful building materials. During the NASA 3D printed habitat challenge in 2019, teams built 1/3 scale representations of habitat concepts for the surface of Mars using 3D printed techniques that would use the Martian regolith. All these experiences that I've kind of gone through you with, as well as many more that I don't have the time to go through, have shaped what I consider my opinions of what space architecture to be. But it all started with my time at CICSA. So in summary, as a young Skywalker in 1988, what I thought space architecture was something that terrestrial architecture wasn't, but I wasn't quite sure what that might be. It was basically educating myself as an architect to tackle different design challenges in a unique environment. It provided me an opportunity to grow as a designer, and it was not included in the engineering mix of planning for human spaceflight. The focus at that time was on surviving and the safety of the crew, as well it should be. And as a current wiser Yoda in 2023, what I think space architecture is, I feel it's a discipline that teaches you by looking to the future. It can inform you about the present. It's about the importance of the inclusion of the human being as central to the design of complex technical solutions. It also fosters creative freedom since it's still an emerging field. The importance of our role, as you'll see from some of the other participants here, as mentors and educators for the next generation will enable the growth of space architecture as a profession. It's an important and essential part of the process of designing for future space habitats that promote thriving in addition to surviving. Thanks so much, and I'll turn it back over to William.
Thank you, Larry. That was a fascinating profile of your background and your achievements. I can't wait till we get to the Q&A section. Now we're going to hear from Chris Kennedy.
Thank you, William, for the introduction. I'm Chris Kennedy, and I'm honored to be included in the Space Center Houston Thought Leader Series program. Space architecture and space architects have the responsibility for human safety, health, and welfare pertaining to their endeavor of humanity's exploration and settlement of space and becoming a multi-planet species. During my 30-year career at NASA, I've had the honor of working with many very smart people, much smarter than I am, at NASA and with the international partners. I was honored to work with several Apollo astronauts as well as ISS astronauts, most notably Buzz Aldrin. Early space system designs focused on humans surviving in space off planet Earth. 60 years ago, we did not know all the risks to human health and how to survive in space. ISS became the human research platform for this to study humans in space. The future of space exploration and settlement will require humans to thrive in space, not just survive. Their physiological and psychological well-being. Space architects, human-centered design, and best practices pertaining to designing healthy internal architectures, the internal environment, lighting, color, materials, etc., are key to long-term success. This will require a paradigm shift from surviving to thriving. Architecture has evolved alongside humanity, from its early beginnings as shelter and protection from the environments, such as caves, cliff dwellings, and nomadic shelters in the forms of sticks and skins. Humans have evolved, and so has architecture alongside of it. We are at the tipping point of space commercialization and a space architecture convergence to enable humans to become a multi-planet species. Nature is a part of the human DNA, and biophilia is about bringing nature into that built environment. Patterns found in nature comfort humans, like wood grain patterns, plants, lighting, art, color, and so on. It has a positive effect on human beings. It stimulates the senses and promotes active psychological and restoration, satisfaction of these basic human needs. There are many definitions or several definitions of what space architecture is. Basically, I feel it is the theory and practice of designing, integrating, and building of inhabited environments to enable humans to thrive off planet. Architects have the responsibility for public, quote unquote, human health, safety, and welfare, which is part of the architect licensing requirements within that built environment, whether it's here on Earth or in space. Space architecture is like its cousin of terrestrial architecture in that it is a holistic critical thinking, always designing a thing by considering its larger context. As Saren, the Finnish architect, described, a chair in a room in a house in the environment in a city master plan. So in space, it's like the light in a galley, the galley in a habitat, the habitat in a surface research base, that base within the lunar exploration mission, and that lunar exploration mission in context of lunar settlement and master planning. Space architecture is different than conventional terrestrial architecture, however. Programs and projects are typically led by engineers rather than architects, with a focus on surviving rather than thriving. This requires use of pressure vessels, humans living inside noisy machines, similar to submarines in some cases. So long-term isolation, confinement, and distance from home are some of those stressors on humans. So it is important to think about the psychology of the internal architecture for the longevity of space exploration. When considering human exploration and settlement off planet Earth, we have to understand the target destination and that natural environment. Space architects will enable humans to expand human presence throughout our solar system. For humanity to be successful, we need to establish sustained human presence and become Earth independent by utilizing local resources, analogous to exploration and settlement of North America by European settlers. There are many elements and systems to architect and integrate across the surface architectures. First and foremost is to account for the human as a system and understand the human-machine interfaces. Space architects have this innate skill and leadership to innovate, design, integrate, and test human-rated spacecraft capabilities and systems. During my tenure at NASA as a space architect, I derived with a notional master planning and zoning strategy with 5 basic zones: the mission, architecture, objectives, the site, the infrastructure, and the base growth will dictate the surface master planning. Strategic thinking and the end state configuration needs to be considered to enable permanent human presence and sustainability. Critical infrastructure, utility distribution, and future growth are critical to lunar-based master planning. During my tenure as a space architect, myself and other space architects derived what we call a space habitat or structures into 3 classifications. Class 1 is the pre-integrated modules or spacecraft, and they're typically the hard can human-rated spacecraft that we've been seeing and using for the past 50 years. They're engineering-led and dominated, and the focus is on survival, not thriving. A Class 2 is a prefabricated on Earth and destination deployed, such as an inflatable structure that Larry mentioned, a transitional blend of engineering and space architecture. Class 3 is a in-situ-derived habitat built from using local resources on a planetarium. Additive manufacturing and 3D printing capabilities and robotic systems are used to build these structures. This is where space architecture leads the design and engineering capabilities. The key characteristics are noted in the table. This is an example of a Class 1 pre-integrated module. They are designed to be pre-integrated and delivered ready to use. It is enabling a mobile exploration architecture that Larry and I designed during the Constellation Architecture team studies in 2008-2009. These Class 1 pre-integrated modules, such as the ISS module, have been heavily dominated by aerospace engineering design efforts. These Class 1 modules are lower risk, but limited by launch vehicle constraints. The Lunar Gateway and Artemis program is dominated by these types of prefabricated, pre-integrated, ready-to-go structures. This is an example of a Class 2 prefabricated deployable inflatable structure. They require deployment at the destination, outfitting, and checkout. They are higher risk, though, than the Class 1. I was the lead architect for the TransHab project in 1999 to 2000. TransHab was initially designed by a Tiger team for Mars transit and then later adapted for ISS habitat capability. Interestingly, I started off my career at JSC in 1988 working the lunar-based system study and designing inflatable habitats for outposts and bases. Tensile fabric, technology, and structures have also fascinated me from my early days at the University of Buffalo, and I was inspired by Bird Air Company tensile fabric structures. These are examples of Class 3 in situ derived structures or habitats. The Class 3 structures are a tipping point for space architecture, in my opinion. Innovations in automated additive construction and large-scale 3D printing robotics processes and techniques are leading the way to built-in place in situ derived structures and architectures. The Icon company is innovating construction robotics and techniques required to prove out these processes and off-planet human rating and occupancy certification of these derived structures prior to human occupancy. Space architecture is at a tipping point, and numerous traditional terrestrial architecture firms are now getting into the space industry, such as SOM, Blue Origin, and BIG. Many space companies are recognizing our value and beginning to hire space architects. Architects are natural leaders, integrators, and have the system engineering integration skills needed by many space companies. However, many space companies still treat space architects as interior designer or artists. Space architecture is transforming the old school aerospace habitat survival designs by placing emphasis on holistic designs, human-centered design, and human system integration. International operability standards are being set for gateway and lunar systems, similar to how international building codes for architecture is used here on Earth. I have been talking with the National Council of Architectural Registration Boards, who governs terrestrial architects licensing and standards in the US, and the American Institute of Architects about the upcoming and new budding industry of space architecture. They are now beginning to recognize this as an emerging industry. Space architecture is trending to the forefront of aerospace industry as humans push to become a multi-planet species. Space architecture is a renaissance. It is providing human shelter, protection, physiological and psychological well-being of its occupants. As previously discussed, architecture has evolved alongside humanity, and nature is part of our DNA, and we need to take it with us. The psychology of internal architecture is paramount for long-term success. Space architecture is creating a paradigm shift towards humans thriving in space. So I want to close with thinking about where your journey begins with an inspiration, and dare you to dream, be inspired, inspire others, and take up this challenge of space architecture. You must have the desire, drive, and determination for success. Thank you so much.
Thank you, Chris. Fascinating comments. I have so many questions for you. I can't wait till we get to the discussion period. Now we're going to hear from Brett Montoya.
Hi, everyone. Thanks for the introduction, William. Thanks, Larry and Chris. I know I could count on you to teach us some lessons. Now I'll just try to take you guys on my journey. So I'm excited to be here today, representing the discipline, and I'm excited to share with you all my experience. I've had a lot of fun in the past 7 to 8 years since I entered this field. At times, it actually seems like it's too much fun. I have a lot of moments where I have internal reflection. I just say to myself, I can't believe this is my job. I'll try to show you why. There's definitely not enough time in here to show you all the cool stuff that I've been a part of. But I'll start with my experience at SICSA. So I started grad school at University of Houston in August 2015. I grew up in Virginia, and I actually came to Houston to study aerospace physiology. I had a bachelor's of science in biological science, and the University of Houston was offering a program, a graduate level program called Human Space Exploration Sciences, which focused on the biological impacts of spaceflight. It was a perfect fit for me. But when I got to the university, serendipity took over and I discovered SICSA. I met the teaching assistants, I toured the facilities and saw all the student work, and it changed my life. This was very exciting. It was all new. It was exactly what I had been looking for. And there were skills on display here that I had to have. So when I started at SICSA in January of 2016, I had a ton of catching up to do. But SICSA had great staff, and I was insatiable. I learned design tools, 2D softwares, 3D softwares, sketching, architectural programming, everything I could get my hands on. And simultaneously, I was learning about human spacecraft design, functional allocations, task analysis, spacecraft systems, structures, getting power in space, moving air in space, dissipating heat in space. The list is incredibly long. I was able to leverage all of my knowledge, my existing knowledge about the human body, which is also a system of systems. So I already understood the complex relationships of systems working together. And my first project attempted to marry those two concepts. What happens to your body in space, and how we can design to better understand that. So I did a design for a lab hab where we created a large space to understand what was happening to the human body. We had never spent significant periods of time orbiting cislunar space. So that was my target, understanding the radiation environment, understanding the isolation of space, understanding what all of that meant together for a crew of 4 for any extended period of time. So during that first semester at SIGSA, I also joined a design competition for the single-person spacecraft. I started the competition solo. For perhaps the first time in my life, I used design tools to create a feasible and inspiring solution. I only inspired one person, but that was enough. I got the assistance of my TA, he joined my team, and together, we worked together to create what you see here, a solution to a problem. And that is really a core function of space architecture, providing the vision with enough feasibility to convince others to help you make it happen. Space is incredibly difficult, and none of us, no matter how talented, are going to achieve it alone. So in the interest of time, I'll move on to my experience at NASA. I had a great time at SIGSA, but I've had an even better time at NASA. So I'm going to highlight some of those experiences. When I started at NASA, I was working for the Future Capabilities team. I was actually working with Chris, looking at an architecture for a station in cislunar orbit. And that's illustrated in the image in the top left here. We did a bunch of internal layouts, looking at different ways to package and organize the systems, the cables, and the ducting runs, and the crew volumes as well. We ended up down selecting one of those designs, and we built it to demonstrate the concepts that we had come up with and to show people the actual volume. And you can see that in the image in the top right. During this time, we were also looking at virtual reality as an alternative to physical mock-ups for this stage of design. It showed some promise and provided the one-to-one scale that we needed. We were able to iterate rapidly and look at multiple different configurations without having to build using physical materials. So that also saved us some money. This was a new approach, so we tested it a couple times. You can see images on the bottom here compare a digital version of the mockup that we built to the physical version of the mockup that we built. And we later went on to write a paper exploring the findings. We learned a ton during that effort, so we iterated the design for a bit, and then we built a new mockup. This time we had crew live in the mockup and perform day-in-the-life tasks like controlling a robotic arm, performing an ultrasound, or setting up the personal hygiene area. And this was the first time I got to work with astronauts, and was definitely one of those I can't believe this is my job moments. Right around the conclusion of that effort, NASA started getting serious about the human lander system and the return to the moon. And I got pulled into a team that was working the crew cabin component of the human lander system. We were tasked with creating NASA's reference design. And reference designs are something that I've been a part of throughout my time at NASA, and they're used extensively to better understand the requirements and challenges of designing a spacecraft. And ultimately, they make NASA a smart buyer when tasking a partner, commercial or international, with creating a vehicle. So one of my team members, his name is Zach, he's also a SIGSA grad. He and I got to work on this internal design together. And here's a look at our concept. This was another one of those, can't believe this is my job moments. So by this point, we had fully adopted virtual reality into our design process, and we were making use of its power to get feedback on our design early and often. Pictured is one of our astronauts evaluating our reference design. So throughout this time, the Gateway concept had been evolving and getting closer and closer to flight. This is a recently released illustration of the Gateway concept, and as you can tell, it's come a long way since the first image that I showed. Along this journey, my team and I have done several of the reference designs for this integrated vehicle, most recently the airlock. We've also performed routine evaluations of the internal layout for the integrated stack, which is really rewarding because we have a lot of partners working on the designs of these different modules, and they go off and they increase the fidelity, and then we bring it back together and we look at the integrated vehicle and what those operations will look like. And it's really a blessing to be on the cutting edge of that. Here's a peek at one of the analyses that we perform. Pictured here is an engineer looking through the window on one of the modules. We do assessments to see with different window designs what you can see. Are you going to be able to take a look at the exterior of the vehicle and assess the condition? Are you going to be able to perform deep space science? Are you going to be able to look at the moon? Are you going to be able to see Earth? Virtual reality is a really fun place to tackle some of those questions early in the design process. All right, my last few slides here kind of bring us up to speed and show some of the more recent work, which has been focused on establishment of Artemis Base Camp. The image shows the vision. It's a really promising vision. It's really exciting, but there's still a lot to figure out. Here's an astronaut trying to figure some of that out. Big thanks to the astronaut pictured here for posting all of these pictures on his social media so that I can share them with you today. These pictures are from an analog mission called C-Test, which just occurred last month at USC Dornsife on Catalina Island. During this mission, we simulated several approaches to logistics transfer between elements on the lunar surface. This is a very difficult and challenging problem that we have to overcome to thrive on the lunar surface. And then lastly, I have a picture with two of my teammates. This picture was taken in front of one of our mock-ups right before it was dunked in the ocean to support this testing. This one's a tribute to my team back at the Center for Design and Space Architecture, and also a tribute to all of those who have helped me get here. It's been a truly exciting time to be a space architect, especially here at NASA. Thank you.
Great. Thank you so much, Brett. That was so interesting to hear about your background and experiences and to see some of the testing you have underway. And I'm delighted now to welcome Paolo, who will be our final presenter before our discussion. Over to you, Paolo.
Thank you very much, William, for the kind introduction and for having me. It's an honor to be part of this incredible event. Before diving in deeply into our discussion about space architecture, I would like to briefly introduce myself and, by doing so, some of the work that has led me here today. As a research assistant at the University of Houston, I've been working for nearly a year on a virtual reality-based project, where I've been building the spacesuit mock-ups you see me wearing in this video. As part of a larger effort to streamline the space architecture design process, making it more iterative and with a self-learning process to avoid design errors up front. It's great to join other space enthusiasts, an audience that might recognize this room. This is the original Apollo mission control room that Space Center Houston restored a few years ago. As a longtime space enthusiast myself, I am the proud author of the world's most accurate virtual representation of this pivotal location for human space exploration. In this model, every control panel, switch, display, and even ashtray has been accurately reproduced. This has been a research effort that has lasted many years without even stepping into the real room in Houston. Today, this unique 3D model is also part of a popular spaceflight simulator called Re-Entry, after its Norwegian developer and a friend of mine decided to use the model to create this one-of-a-kind experience, enabling players to control their simulated missions in a similar fashion Apollo flight controllers did back in the 60s. through a realistic and historically accurate scenario where every bit has been accurately reproduced. Looking at the future of the mission control room concept, this is another project I've been involved in, where I was tasked by conceptualize a Martian mission control center to be part of a future interplanetary colony. The idea is to bypass the inconvenience of relying on Earth-based assistance, providing a real-time and in-situ mission assistance and strategic planning capability, performed through the implementation of a modular and reconfigurable 360 degrees video immersion room. A future to be built in space and on the planets that will necessarily have to be designed with a long-term vision in mind. With this aim, I'll introduce the project that to me is the most important in light of our discussion today, encompassing my vision of space architecture as the leading discipline for the future of humanity in space. Any conquest is the result of proper resources management, and in space, the most important resource is the orbital mechanics, the real key factor to access the material resources out there. This project, developed within our space architecture faculty at SIXA, is based on the idea that resources on the moon will have to be made available for customers operating directly in space, incrementally cutting off reliance on Earth-based resources. An initial series of missions and modules could be placed at Lagrange point number 1 between the Earth and the Moon, with the aim to becoming a gas station of moon-mined propellant. Such moon-mined propellant will be brought there with a series of vehicles called space tugs. Every space tug that will be part of the system will be connected with a container-like module that we see now being delivered by the SpaceX Starship to be filled on the moon with ISRU-obtained propellants and other resources, depending on the market needs of the future. The space tug leaves L1 on its first mission, also carrying a couple of rovers to be left on the moon to be operated by the future lunar crews in situ. Such rovers are meant to be used to refuel the space tug and its hybrid propulsion system, designed to work with a mixture of solid and liquid propellant, not to impinge the fuel reserves that are meant for customers at Lagrange point number 1. The trade-off is an added lunar production line for solid propellant to be mined from regolith, in exchange, of course, for a much lower use of commercially viable propellants for the space tug itself. The container module will be filled with propellants like liquid hydrogen and liquid oxygen. Here we see the refueling process of the space tug, while the container module will be refueled with a system of pipelines that run all the way down the space tug itself, thus avoiding the problem of unloading the container module entirely. The rovers are left on the moon to assist other incoming space tugs, and as missions progress, more and more storage capability is built at Lagrange point number 1. Ideally up to a nearly 1,000 tons of fuel storage capacity, all with a series of modular parts that can be replaced with relative ease, providing redundancy and many docking ports for customers to be served. The space tug can then become a workhorse for cislunar space and its customers, combining the fuel shuttling activity from the moon with what the market will demand, given the vehicle's inherent flexibility. One big vision for the future will be when regular ferries like these will carry thousands of tons of resources from the moon into space, possibly even back to Earth, all done with a reliable fleet like this to serve a series of platforms at the various Lagrange points between the Earth and the moon. I'm looking forward to explaining this concept further as part of our discussion and its implications for space architecture, of course, as there is more data and facts to it than just mere renderings. So with this, I'll conclude my speech, and I'll thank you again, everybody, for inviting me.
Thank you, Paolo. That is absolutely fascinating. And also the concept of multi-vehicles simultaneously launching and moving near one another in space is, I think, a really interesting concept. Absolutely fascinating. So I wanted to begin our conversation today by asking all of you, how did you become interested in space architecture? We know about your professional development, but did you imagine yourselves pursuing this in your early years of life? And was there some point of inspiration that got you interested in the space program and pursuing this pathway?
Okay, I'll be quite honest. There were no inspirations early on, but I think in terms of at the time of life that I was at when I was interested in exploring new roles as a designer, as opposed to the idea of particularly with space. I think Brett mentioned it quite a few times. He couldn't imagine where he was, what he was working on. It was the same thing for me when I first got involved with SIXA, was that it was a whole new area that you had to educate yourself in terms of the environment you were designing for, the differences that made in terms of your approach to design. So I think in terms of my case, my interest sort of evolved over time, but it was from a design standpoint rather than the idea of particularly space.
For me, I've always been interested in architecture, and I was always interested in technology. And like I mentioned earlier, bird air structures and tensile fabric structures were fascinating to me. So when I went back to go to graduate school at the University of Houston, I stumbled across the SIXA program. Wasn't SIXA at the time, but actually Larry and I started at the same time, and in the same at the same time at the university, and it was fascinating to me, and it just hooked me to where you know, we've watched the movies and about space and this that, but this was an opportunity to actually participate and shape the future of humanity and be part of NASA. So for me, it was just too good of an opportunity to miss, and you know, I was thrilled to jump in with both feet and see where it took me.
How about for you, Brett?
Sure. I regaled some of the story in my bio, but maybe we'll back up even before that. I've always known that I wanted to contribute to solving problems for the betterment of humanity. It's always appealed to me, and it's always been driving me to find something that was new and cutting edge, something where not a lot of work had been done. And when I left undergrad, I thought like cancer biology was where I was most interested, because that was solving a lot of real world problems. It was a very difficult problem. It was unique to each individual with each different type of cancer, and that sort of problem has always appealed to me. That's a very hard industry to get into and requires a lot of additional education. So before I went down that path, I looked at other very difficult problems to solve in the biological and physiological realm. And that's what brought me to space. It's the next frontier. It's unlike any place on Earth. So what harder problems could you find than going to space? And that's how I wound up here.
And Paolo, what was your inspiration to pursue this pathway?
It's a fun story. As you probably have been able to see through my presentation video, I've been a long time space enthusiast. But besides this, I've always wanted to direct some project, some very important project that could make a positive difference for humanity. I was a product design. I actually enrolled in aerospace engineering in 2017 here in Italy. A year after that, I realized that that was not what I wanted to do, not because I didn't like aerospace engineering, but because I thought it wasn't enough for me. I wanted to be like an orchestra director with my projects. So overseeing the entire thing and providing the vision. So I switched to product design a year after. I wasn't satisfied with product design as well. And one day while I was coming back from university, I was on a train, and just by mistake, I happened to see some pictures that were posted by a friend of mine on Facebook about this Sasakawa International Center for Space Architecture. And I thought to myself, what's space architecture? I never heard of it. And I went to the website, and in about 5 minutes, I knew that that was my destination. Now, 4 years after, I'm here and happy to be here. And by the way, the friend that who I didn't know at the time that posted those pictures back then, 4 years ago, is now a colleague of mine. So I guess the world is really tiny. But again, it's great to be here, and also I really believe that this faculty can really push the boundaries for humanity in space and also to Earth, because we have to remember that we design in space, but also for the benefit of mankind here on Earth, because space and space exploration has so many technological and sometimes even philosophical spin-offs that have important consequences all over the world.
So interesting that you all have had different pathways and found different ways of being inspired. I have a question about a lot of the work you do, of course, requires developing models and testing those models. And I want to use as an example the current CHAPEA, which is creating a habitat for simulating life on Mars. And so what are your thoughts on things that we can do when you actually have humans in a habitat like this? Do you, in your models, intentionally introduce anomalies, especially when you have human subjects, to kind of understand how someone will respond in those scenarios? Because to me, my impression is that you have to think through every possibility, right, of things that could potentially go wrong or how humans may respond in a certain situation. Because to me, being a human explorer in space, you're really a master problem solver, because something always goes awry. Something always doesn't function the way you had anticipated. How do you develop a hierarchy for addressing that?
I think the challenge of space architecture to deal with what you just brought up is that as, quote, an architect, you're wanting to provide an environment for the crew members that is satisfying enough that it can support them psychologically, physically, et cetera, over a very long period of time. On the other hand, you do have to design for that off-nominal situation, that extreme, such as a fire event or something that is requiring exit from that habitat. So you have to have both of those in play. And I think what we tend to do is sometimes focus on one rather than the other. And the importance of the off-nominal situation is probably the most important one, right? The safety of the crew. But then, as an architect, you want to introduce elements of the design that are comforting to them at the same time. So I think with models or mock-ups, that's kind of what we try to do when we work with the crew on specific design features.
Yeah, I'd like to add to that as well, Larry. When I was running the Habitat Demonstration Unit and we built a prototype, took it to the desert for testing, to me and for our team, it wasn't necessarily so much about what the exterior looked like of the prototype, but more about the interior operations, working with mission control, running these anomalies, understanding the design and where its flaws are, so that we could better, as Brett was saying, better be more informed about who is going to build it later and what we wanted them to build, and to work out those bugs and figure out where the problems were as best you could, and then design or minimize those risks. And so, I think virtual reality has come a long ways and really helped us to explore design options quickly, but I still feel that the full size mock-ups and capabilities are needed for crew to go live in and test. And I think that's essential to really iron out a lot of these designs.
So I'm glad you brought up the mock-ups, Chris. That was definitely my answer to this. Essentially, the testing part, simulating what conditions you are going to be under to the best of your ability. I think that is where you find these issues. And the beauty of testing, especially in analogs, is that you are in a real world situation. It may not be the same one, but like, for example, C-Test, which we just did, they were scuba diving underwater. They were on an island as well. So there's an isolation part of that. There's a dangerous part of that. It's one of the reasons that at NASA, we prioritize expeditionary training for astronauts so that they can get in these circumstances where they are not necessarily safe. We do everything that we can to make sure that that if something happens, they're taken care of, but there is an element of risk there. And when you're doing these things in a real world scenario, you can't control all the elements, and some of those off nominal situations start to crop up. And the more you simulate, the more of those problems that you catch, and the less of those problems that you'll catch when you're in space.
And I would like to add just a few things based on my relatively small experience, given the rest of the panel, but I think it's still relevant. The work we've been doing at SIXA during the last few years, during this last year when I've joined the team, I've been working on the mock-ups that you have seen in the introduction video. I've built a spacesuit mock-up to be used in that VR lab. That, I think, is a good example of the transition we're trying to make today from only physical models to, even if not totally, but at least partially, virtual models. The aim is to be able to iterate much faster, because physical models can take a lot of time, a lot of effort, and there's no point in wasting months or even weeks and thousands or hundreds of thousands of dollars into mock-ups that just to find out that they're wrong at the end of the process. Any design change that is retrofitted at the end of any cycle is in fact an added cost. So if we're able to simulate that upfront, we're able to not only provide savings, but also provide a much quicker way to improve designs and learn from our process, to stimulate that self-learning process that is so instrumental to the success of the space exploration business. Another thing that I would like to mention is that we've made I will take advantage of history, of space history now. More than 50 years ago, we had the Apollo 13 accident, and during that flight, they had to retrofit many parts of the spacecraft. For instance, one of those parts was the oxygen filters, and there was a difference between the connectors that were on the lunar module versus versus the filter on the command module. A cylinder type versus a square type of filter. That kind of thing, I hope, it's not only detail. We have to be able to think those things up front to provide some sort of cross-pollination in order to be able to prevent retrofitting problems that might arise in the future. Because any design that is so refined that doesn't leave any space for any retrofit, I think it is a design that is much more prone to fail.
So interesting. Thank you. Something that you all spoke about, which is so fascinating, and I think it's a perspective we don't always hear, is having people-centered design, right? Because of course, I think everyone understands that the vehicles you're designing for human space exploration are intended to keep their crew not only alive, but thriving in some way. But I don't think that many people imagine how much information you have to amass and analyze to understand how are humans going to function within a particular space. And you actually, I think it was Chris, introduced a new vocabulary word for me, biophilia, which I'd never heard before, which is absolutely fascinating. And so how do you create that hierarchy of priorities for someone in space? Is it based upon the goals of the mission? Is it based upon the duration of the mission? So what are the factors? How do you approach a kind of people-centered design for a particular vehicle for a mission?
For me, I think space architecture or any project starts with a vision and then a mission statement of how to enable that vision, and then you develop goals and objectives, and those objectives become how you implement that vision. And so integrating the human as a system, and thus human-centered design, is really important, because now you take into account the human-machine interface, the human interface to all aspects, and making sure that the human can go in and replace a filter and fix things. And so all that is part of the analysis, the design analysis process. And it's not just an architect there's a whole team. There's a multidisciplinary team of a lot of experts coming together with their ideas and their opinions on how to improve a particular design. So there is a systematic way to walk through a process of the design and then reviewing the design, evaluating, and then reiterating the design. And this is a part of what SICSA teaches, is that process of going through and methodically looking at and understanding the user in that environment. What is the user doing? What are they doing for their operations? Are they, and what different aspects or tasks are required by the humans within that particular mission. So once you go through all that, you have a better understanding or a concept of operations to better look at the architecture and design concepts and alternatives to meet those needs. I'm sure other folks here also have some thoughts there.
I would just follow up on that. I think it's really good. Chris just brought that up. I teach at University of Houston at SICSA now. One of my lectures is on human-centered design. And a key aspect of it is asking the students to basically do a concept of operations, do some storytelling, write down the story of how you putting yourself in the place of the person, the crew member inside of your concept is actually gonna use it. How are they gonna experience it? In other words, write the first chapter, write the second chapter, the third chapter, and start there, because what you find is that if you start from the other point of designing something, you end up having to basically instruct the crew how to use something that they had no part in basically driving out the way that it looks and the way that it functions. So I'll just tag on to what Chris just brought up. I think your initial question is, what can you do to make someone more aware of that the human is the center of it? I think the center of it is actually starting with a storytelling. Again, a concept of operations.
Well, I wanted to ask another question, and perhaps Brett and Paolo, you could begin by responding to this. Something that Chris mentioned was the development of standards and codes for the human-centered design, which I think is fascinating, and something that's so phenomenal about human space exploration is the benefits to all of us here on Earth. Are there things that you can cite that out of the work that you do that are benefiting us here on Earth, or have provided us with insights about our lives that our viewers should be conscious of or could apply to themselves?
I think I can start, maybe.
Yes.
I think, just following up on what Professor Toups and Professor Kennedy said before, I think I see ourselves as orchestra directors. I probably said that before. I think our aim is to, direct a project overseeing a multidisciplinary environment, being able to talk with people who work in very different environments and have very different tasks. Like an orchestra director, we don't need to be able to play all the instruments, but we have to be able to know when a note doesn't work in the composition. So that's, I think, my view on the space architecture in general, of the space architecture approach. As Olga Banova, who is our program director, said in her book about space architecture education, space architecture is a lot about the process. Engineering is sometimes, or often, is about the product. We try to be as general as possible to apply our knowledge and capabilities in as many projects as we can. To the normal people, to the people who don't know anything about this, I meet a lot of people who don't even know anything about space architecture. I think the most important lesson to be learned is that you never stop learning. So you don't have to be fooled by your own prejudices. You have to be able to understand that your knowledge, I think I can quote Socrates. I think he said that education is only the measure of how much you don't know. And space architecture is a lot about that. We can always increase our knowledge, but also we but also we have to be conscious enough that that knowledge can always be increased.
All right, I can follow that up. And the subject was, what are we doing in space that benefits us on Earth? So as a space architect, we design habitats for living in really extreme places. If you look at the news almost any day of the week, you can see some extreme weather that happens here on Earth. Like we're living in, we joked before the program about getting the first rain in like a month here in Houston, and that's had some pretty dramatic effects to people's HVAC systems, for example. Like we have insanely detailed and difficult to design life support systems for spacecraft. And we're always trying to be more efficient so that we're using our resources better, the quality of the air is better so that our astronauts perform better. All of that technological innovation can be applied back to our homes on Earth.
I would like to follow up on the codes and standards question pertaining to space, but also here terrestrially. The interoperability standards were developed with international partners so that you could have ecosystems cross-pollinated between ESA, Russia, and the US, for instance, and Japan and others. Here on terrestrial architecture, we have the international building codes that have really moved to better understand the built environments and the effects on its occupants, creating healthy buildings. The WELL building standard is a performance-based system for measuring, certifying, and monitoring features of the built environment for that impact of human health and well-being through air, water, nourishment, light, fitness, comfort, and mind. So I could see how kind of the marriage of these two, both terrestrial and space architectures, are coming to the forefront. And if you think about healthy buildings, well, certainly we want healthy buildings or spaces for our astronauts to live in. So I do see that there's a convergence, as I mentioned earlier, between terrestrial architecture and space architecture. Thank you.
So I think your question is a good one, William. I think the benefits of looking to space as a design challenge can actually benefit Earth in terms of from an educational perspective as well. In some other teaching that I do, we use the challenge of designing for zero gravity or even Mars for industrial design students, let's say, that takes them out of their comfort zone, sort of what Paolo just mentioned, right? It's kind of what they don't know that stimulates their creativity. So they can design a very creative, innovative approach to conservation of water, to the idea of things that are new material kind of ideas and things like that. And what happens is that those students then take those ideas they've generated to solve a space problem and apply it to a current day situation on Earth. And it's really a stimulating kind of thing for them as a designer, not as a quote space architect, but it benefits us here on Earth because you find a way to provide a stimulating, innovative approach to a challenge we have now on Earth.
Can I just point out a thing real quick about the codes and regulations? I think that we are all subjects to codes and regulations, but given our multidisciplinary approach, I think we can also have a unique role in guiding the legislation and the codes to some direction that can be to the betterment of space architecture as well. So we're not only the subject of codes and regulations, in my view, but also we can help the design of such regulations. Thank you.
Well, we have reached the end of our allocated time, and I have so many more questions. So I want to thank our panelists today for all of their incredible insights and sharing their knowledge and experience. Heartfelt thanks to Larry Toups, Chris Kennedy, Brent Montoya, and Paolo Mangili. Hopefully we can get together at another point to continue this fascinating conversation on space architecture. I've learned a tremendous amount. So again, thank you for the amazing discussion, and thank all of you for joining Space Center Houston's Thought Leader series on space architecture presented by UTMB. To our listeners, please visit our website at spacecenter.org to view past Thought Leader programs, and we look forward to having you join us at future programs as well.